Hey, Elena.
What's it about?
It's about electron configuration.
You would record how bad you are at teaching?
Excuse me?
Okay.
Oh boy.
Are you gonna teach me about Einstein splitting the atom?
No.
Oh, this is boring.
So Rutherford is
Rutherford.
Rutherford. I don't know.
I thought it was Rutherford. You said Rutherford.
I don't know. Anyways, so he came up with an electron model. It contrasts the pudding model. So there is this model, and that shows that protons are in the center and that electrons are floating around. He came up with a suggestion on our knowledge of atoms that we have today. He suggested that at the center are protons, and around them electrons sort of orbit or float around. This contrasts the plum pudding model. Stated that there was just sort of electrons and protons and whatnot all inside, an atom, and they were just in there like pudding, and that they mixed together. Rutherford came up with the idea that instead, electrons are around the center proton. Say Neil.
Neil.
Neil?
Neil.
Say Niels Bohr.
Niels Bohr.
Niels Bohr.
Niels Bohr.
Niels Bohr.
I'm doing it by myself.
Say Niels Bohr.
Niels Bohr.
It's not bored, it's Bohr.
Niels Bohr.
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 Yeah.
Niels Bohr.
Yeah? Alright.
Yeah.
Another guy came along and made one just a teensy bit better. So this is another picture that you should probably recognize if you've seen electrons and protons and atoms, basically. And this one just shows that electrons are around the center in levels, and that they're orbiting protons and neutrons, which are in the nucleus. Then, another man, Neil Bohr, came up with another suggestion for what atoms should look like. This one was more that atoms are electrons orbiting protons in levels and orbits, and that they're not just random everywhere.
Yeah.
Try to squeeze as many fingers as you can into that first circle.
Don't make me do that.
No, just put as many. If you can only put one, then you only put one. No, put it flat on the table.
Can I rip the table?
No. Why would you rip the table?
I meant the paper. Can I rip the
No, you can't rip the paper. I know, I don't need it anymore.
Oh.
You can finish it.
Okay.
I'll lose that.
Eat my beans!
Put it down on the table flat, and try to put as many fingers on it as you can. Got it. Okay, now take the bigger one and try to see how many you can put on that one. So you can obviously put a lot more fingers around that one because it's bigger, because its circumference is bigger, and its radius, it's all around bigger. Just the tiny one. Try putting as many fingers as you can. If you can only put one, if you can only put two, got it. Now how many fingers can you put around the bigger circle? Just on that smaller line.
Go away.
Hey! Now how about the bigger one? How many finger points can you touch? Yeah.
No, on the inside.
No, she was doing it much better than you guys.
That's not right.
No.
Oh, you didn't explain very well.
Yeesh. Oh, so is it much easier?
Oh,
Right.
mine? I thought you meant the
Go away.
stain.
Yes, that's what. Yes.
Then I could have done it easier.
Hey! So that's kind of what it's like when you have an atom. You have the nucleus, and you got a shell around it that can only hold so many atoms, but the bigger ones are allowed to hold more because they have a wider circumference and they're just bigger around the atom than the nucleus and the protons and the neutrons. Okay, so when you do start having all these complications because it gets so big, then you have to come up with a system. So, with this system, you start using things and you start labeling the shells and the orbitals, and you start labeling the electrons outside of the shell. So first, here we have hydrogen. Hydrogen is simple, easy, it just has a single proton, it has a single electron, it doesn't even have neutrons.
What is that?
What are you looking at now?
Statistical maniac.
What are you looking at now?
That's an S.
Oh, no, that's because there's a reason for that.
Such
So here you can see that it says 1s1, and this corresponds with the atom hydrogen. This is because that first 1 before the S stands for the amount of circles around the nucleus. The second one stands for the number of electrons on that circle. Okay, so this is gonna fit into an S slot, and we're gonna title it 1s1. The hydrogen is gonna be 1s1 because it has one shell and one electron. One shell, one electron. One level, one electron. One level, one electron, and you have it, you title it S. First
Oh, so there's like 2 sets.
shell. Yeah, and so now it has two S1.
That would be 1s2, and then that would be 2s1. So like the second one would not be because there's 2, because the second one would be 2s1. And then if there was a third, that'd be 3s.
Yes,
Or whatever number.
perfect. So, and this is all the extended version.
Ah, you're making me learn.
Now, when you're talking about the S's, can only have 2 electrons. So you have to have, so if you get to then something like boron, where it has 3 electrons on the outside,
What does S stand for? Then?
it's just the first, it's like the primary grouping. This second one has 4 pairs. 1 pair here, 1 pair here, 1 pair here, 1 pair here.
Yeah.
One of these is an S pair, meaning it's like a primary pair. S stands for super, let's say. The other 3 have to be other pairs, lesser pairs, like P as in, what's some sort of derogatory P word that means less than super?
Poor.
Yeah, P stands for poor. So when you have pairs in levels, since this only has 2 electrons in the first level, then it's automatically an S pair. Now this one has 4 pairs, and one of them has to be S, and the other 3 have to be P. They have to be poor. Well, one of them gets to be super.
Why are they naming it P and then?
I don't know where the letters come from, but it's like this.
Go back to
Think
the
of it like
thing,
this.
'cause it has-
See, these are called S's, and these are called D's, and these are P's, and this is F.
More complicated one, I probably have to.
Yeah, things like you get sulfur, and you get calcium, and you get argon, and they get all really complicated, and they just turn into 3s and 4s, and then you get into the D's and the F's. So there's a simpler way to do this. There's a way to get rid of all of this right here, and then have just this. And so you label them like this. So you know how you have your P block, and you have your S orbitals, and hey!
Got you.
Can I have that back, please? So this equals AR. So if you wrote AR, and then you wrote for S2, which is calcium. So it's like saying all of this plus this, but instead of having to write all of this, you just write this because this equals this. Yeah, it's like, you know, in math class when you have X plus Y, and if X equaled 3, then it's 3 plus Y.
Yeah.
So it's easier. So it's like saying X equals 3 times 5 divided by 2. So instead of putting 3 times 5 divided by 2 plus Y, you just put X plus Y.
Yeah.
So it's easier. Okay. The Pauli exclusion principle.
Is that because they're negative?
So, because remember how I keep telling you that they're in pairs? Well, they're also spinning, and they're spinning in pairs. So they spin different.
Yeah,
so one spins one way, and the other one spins the other way.
This finger,
Nah.
this finger right here is
Touch your
going-
fingers together and do the exact same motion.
This is going counterclockwise.
Touch your fingers together and do the exact same motion. Now do it. Yeah, no.
Here,
Anyways.
let's see if you can do it.
Oh boy.
Okay, wait. Mind over matter. Can't you do it?
Wait, let me see.
Oh wait, here we are.
It's easier to do it on an object. Now do it in the air, because that's where I was having a hard time doing it in the air. But no, but they still need to evolve like next to each other, like you said. They have to be next to each other.
Okay, wait. Okay, so I went
But they have
clockwise,
to.
counterclockwise, clockwise, counterclockwise.
Don't they have?
Clockwise,
Yeah,
counterclockwise.
yeah. That's the way that it needs to be. Yeah, like that. See? It's hard.
Struggle.
Wait, you gotta do this.
Yes.
Start spinning together, but
So this would basically be helium. You guys are reenacting helium. Yeah.
Yeah, I don't do good with spinning. It doesn't work well.
Are you reenacting hydrogen, Celeste?
Sure.
I feel
Sure.
like I'm confused now.
No, it's cool, right?
Yeah.
So when you get to 11th grade, you won't learn this, and you will feel jaded and cheated. Sometimes things like this are pretty fun. Sometimes they're boring, sometimes they're way too easy, sometimes they're way too hard, sometimes they make your mind melt, sometimes it's like, yeah, I got this, and sometimes it's interesting enough to base your final project off of. So, yeah. Okay, so
Whoa, that looks like something I could never draw.
me too.
I think that's sort of what
Um,
is that?
it's probably just a random atom, but I googled gold
That's
and
a random
silver.
atom?
I googled gold and silver, and yes, right, yes.
If I did look like that, I would.
That's an atom. Yes. Okay.
You realize we're made up of these cool looking things right here.
Yes.
We are those. If you guys have self-image issues, you need to stop Google atoms as you're making it.
Okay.
Atoms. What?
All right.
Are you saying if we split something that we can't see, like it's so small we can't see, it makes a huge explosion? That means
Or a lot of
actually
energy.
hold the power of an atomic explosion. Think about it.
Yeah.
We have the power to make an atomic explosion.
Well, yeah. Although usually they do that with uranium and plutonium, and we don't usually have those inside of us. Okay. All right. Yes, we have that power inside of us.
Oh, I'm gonna blow up so much stuff.
Actually,
now.
you know what? That's usually when you take neutrons away from the nucleus, and we don't usually have big enough.
Can you ring it for me?
All right.
Continue.